Okay, so now we want to answer some questions. We want to know whether if when alpha is not equal to 0, what would be the order of the accuracy of this approximation that we have here. If it is not 0, what would be the order of that, and what would be the highest order term in the truncation error? Okay, so I want to raise an interesting question, and the question is, can we choose alpha such that the order of approximation increases Can we choose it alpha such that it to increase the order of approximation? Is it possible to do that? And we want to answer this question. And can we choose it kind of a particular value in order to increase the order of the accuracy, for example, to delta x cubed, not even more than this, even more than delta x squared. We wanna investigate that here. Okay. Okay, so first we have two equations, right? One is the governing equation, the second one is from the truncation error. So the governing equation gives us v u prime I minus d u double prime I. This should be equal to what? It should be equal to 0, right? Because it is exactly this. V du over dx minus d square u over dx square, or d u double prime, right? So we expect this governing equation to be 0 according to our problem statement. And so this is going to give us an interesting relationship. And the relationship is u double prime I equals to v over d u prime I. Right? So this is the relationship that we can get from the governing equation. Okay. And this is going to give us another interesting relationship. So let me show it. If we take another derivative from both sides of this equation, so take d over dx of both sides, v over d is a constant. So what we are going to get is this. So u triple prime I is going to be v over d, which is constant, times u double prime I. And u double prime I, from here, we see it is v over d times u prime I. So it's going to be v over d square u prime I. Okay? So a very interesting relationship here. And then I can continue this. So I can write, for example, u for I equals to v over d u triple I, and this equals to, from here, equals to v over d to power 3 u prime I. Okay, so I can write and represent all the high order derivatives in terms of the first derivative and v over d constant. Okay, so this is what we get from the governing equation. And now I want to use this approximation, this kind of relation that we found here, and substitute that into our truncation error approximation. Okay, so let me write that down. So this we are gonna have this. We are gonna have the truncation error. The whole equation is gonna be equal to v u prime I minus d u double prime I plus. So what I'm gonna do next is I'm gonna get take a factor from u double prime I and then write the other terms based on that, right? So here, for example, this term is u triple prime I, right? So it's gonna be v over d u prime I. This term is gonna be v over d square u double prime I, correct? This term is gonna be v over d cubed u double prime I, right? So you can find it from here. For example, u triple prime is v over d u double prime, right? So this is what I wrote here. And u4 is gonna be v over d square u double prime. You can calculate it, it's written here. So I'm gonna factor u double prime here. So I'm gonna have plus u double prime I minus the first term is going to be v alpha delta x over 2, right? So I have v alpha delta x over 2. The second term is going to be v alpha delta x square 6 times v over d, right? So I'm going to have plus v delta x square over 6 times v over d. The next term is going to be the next term I don't want to write this one because these are high order ones, so I'm going to write first this one, which is delta x square. So I will have d times d delta x square over 12, so it's going to be minus d delta x square over 12 times, and this is going to be v over d square u double prime, right? So v over d square times u double prime, which is here. Okay, the factor. And these are first and second order terms plus other terms, which are order delta x cube and higher order terms, right? So I just, instead of these, because these are delta x cube and delta x to power 4, I just write this. Order delta x cube and other higher order terms, okay? So this term is already 0, right? This is the governing equation. I want to make it order higher order, right? I want to make it maybe like order delta x cube, right? I want to find an alpha. This is a question I had. Can we choose alpha such that the order of approximation increases? So here we had already, if alpha is 0, it's going to be order delta x square, and I want to see whether I can retain these terms, but at the same time get rid of all these terms, right? So if I get rid of all these terms, then my order of approximation is going to be order delta x cube and higher, right? So I'm going to write u double prime I coefficient and divide that by 1 over d. Okay. So what I'm going to have is from this, the first term is going to be what? It's going to be minus alpha over 2 v delta x over d. Okay. Then I have the second term. So the second term is going to be 1 over 6 v delta x over d square. And then I'm going to have the third term, which is going to be v 1 over 12 v delta x over d square, and this is from here. Right? I want to set this to 0. I want to set this to 0 so then I can get rid of delta x and delta x squared terms. Okay. So let's see what value of alpha we will have if this situation is satisfied. So before that, I want to define some important number here, which you might hear it in other places. It's called Péclet number or Péclet grid number, which is defined as v delta x over d. The advection velocity over the diffusion coefficient times delta x is called Péclet number. Okay. Just for your information, I'm going to define this Péclet number. And I want to write these based on Péclet number, this sum here, this relation here, okay? So I'm going to get minus alpha over 2. First one is Péclet, P-E plus. And these two are going to give me what? It's going to give me 1 over 12 v delta x over d squared, right? So I'm going to have plus 1 over 12 Péclet grid power 2 equals to 0. So if we choose alpha to be Péclet over 6, then this is going to be 0, and so I'm going to have the order delta x cube approximation. So this is very important. If we are able to actually control the accuracy of this by choosing a proper alpha. So if I choose alpha to be Péclet over 6, which is v delta x d over v delta x over 60 here. So if I put like here v delta x over 60 and the same here, then I'm going to have a delta x cube approximation. So it's going to be order delta x cube, which is interesting, right? It's the same number of points, and just by changing the alpha in this equation, I am able to increase the order of the accuracy. So the answer to this solution is, to this question is yes. We can do that, and if we choose alpha to be Péclet over 6, then we are going to have a higher order approximation. Okay, so I want to go further. I want to go further and ask another question. And the question that I want to ask now is, how about higher order? Can we go further higher? Can we have delta x4, delta x5, or whatever? Just go higher. Can we choose alpha such that to have higher order approximation, even higher than delta x cube? So this is the question that we face, and I want to make. Okay, so let's start. To answer this question, as we know here from these relations, I can say UIP, which P means that the pth derivative is going to be V over D P minus 1 U prime I, right? Okay. So now, based on this, I'm gonna write the Taylor truncation error, the whole truncation error that we have. I will represent it based on U prime I, based on this formula. Okay. So the first one is this. Okay. So I will have this equals to alpha. And I'm going to separate alpha from the other terms. Okay, so here we have the truncation errors. So I'm going to first write alpha terms and then add the other terms to that. Okay, so the alpha will have this and this. Okay, so these will be the terms where I have alpha. So let's the first one is going to be V delta x over 2. So alpha minus V delta x over 2. And then I have U, instead of U double prime, I'm going to write U V over D times U prime. So I have V over D U prime I. And then I have the next term. So the next term is going to be, which term? It's going to be this one. So I have V delta x cube over 24 times V over D cube, because I want to write it as U prime I. So I have V delta x cube over 24 times V over D cube times U prime I and other terms, okay, that have alpha in them. And then I write all the terms that have no alpha. So it's going to be first this one, and I'm going to write it based on U prime I. So this term is going to be the first one. Then I have this term, and other terms. Okay, so first let's start with V delta x squared over 6. So I have plus V delta x squared over 6 times, it is U double prime, so U triple prime. Let me see. Yeah, it is U triple prime, so it's going to be V over D square U prime I plus then it's gonna be v, the next term is gonna be this term, which is v delta x 4 over 5 factorial times vd to the power 4, right? So it's gonna be delta x 4 to 5 factorial times v over d to power 4 of u prime I plus other terms. And then I have the diffusion ones. The diffusion ones are d delta x squared over 12 times vd to power cube times u prime I. So I have d delta x squared over 12 v over d cube u prime I minus the other terms that I hadn't written, but I want to write it here, delta x to power 4 6 factorial v over d to power 5 u prime I plus other terms. And then in the next step, I'm going to divide this by v and substitute the Péclet number definition, which is v delta x over d here. So let's divide that by v. I'm going to get minus alpha. The first term is going to be delta x v delta x over d time over 2 times u prime I. So, and I'm going to factor u prime I. So I'm going to have Péclet. The first term is going to be Péclet p over 2. The second one is going to be, if you calculate it, is going to be Péclet it's going to be v delta x cube over d cube. So it's going to be Péclet to power 3 over 4 factorial plus this goes on and on this list times u prime I. So this is the first one, and then the second one is gonna be, I'm gonna again factor u prime I. So I'm gonna have, the first one is gonna be Péclet grid to power 2 over let me just check something here. V delta x, let me check. V delta x, we had it here. Over 12, if I'm not mistaken. Plus Péclet number grid, and this you have to calculate it yourself because I'm just writing it here. I calculated live, so you have to calculate it yourself to make sure it is correct for the other terms. So it's going to be Péclet grid number over something in the denominator times u prime I and the other terms. And I want to set this to 0. I want to set Taylor truncation error to 0. So it's very kind of extreme kind of behavior. I want to see whether I can completely set the Taylor truncation error to 0, okay, by doing this. So if I do that, then what I'm going to get is alpha is going to be Péclet grid to power 2 over 12 okay, plus Péclet grid power 4 over that thing in the denominator and the other terms, which is just this here. So these u prime i's are going to cancel, right? Over what? Over, in the denominator is going to be this. So I'm going to have Péclet over 2 factorial plus Péclet over 4 factorial and others. Okay. It turns out if you calculate this carefully, I'm just going to write the final solution of this. These two series are going to converge to a very simple expression, very interesting and simple expression, which is 1 over 2, 1 plus cotangent hyperbolic cot h of Péclet grid over 2 minus, let me see, this minus 1 over Péclet grid number. So it turns out if you do these calculations carefully, you will get to this solution. Okay. And what does this mean? Let me just clean here a little bit. What does this mean? So let me maybe highlight it because this is important. This means that if you set alpha to this value, which you can simply calculate, right? You have the Péclet number, which is v delta x over d, and you can calculate this cotangent and cotangent and this the Péclet number here. Then this alpha makes the truncation error 0. What does this mean? When your truncation error is 0, when this term is whole is 0, what does this mean? Think a little bit about it. What does it mean? It means that this finite difference approximation gives the exact solution for the PDE, for the considered PDE. This gives the exact solution. Very interestingly, by modifying and choosing a correct alpha, we were able to make the truncation error to be 0 for this case. I just want to note that this doesn't happen often, but just for this particular example, I wanted to show that you can choose alpha such that to be able to even increase your order of accuracy to infinity, meaning that your solution is exact. Okay, so this is very important point about truncation error example that we solved in this lecture. Okay, so in the next lecture, I'm gonna go through time marching methods like Euler, and maybe after that, if you have time, we will talk about Adams-Bashworth method and other ones like forward Euler, backward Euler. We will surely talk about them. And then if you have time, we will talk about like different time stepping methods to be able to fully solve a PDE using finite difference schemes. Okay. So let's review what we learned today in this lecture. So in this lecture, I started to solve an example, a truncation error example for you. And the question we had was, what is the truncation error or the order of the accuracy for this example, for this advection diffusion equation with the approximation that the question wanted from us, which is variable weighting scheme for the advection term and a central difference scheme for the diffusion term. Okay. So we wrote the approximation based on what the problem told us and asked us, which is a variable weighting scheme and central difference scheme for the diffusion term. Then in order to find the truncation error, we used Taylor series. So we used Taylor series and we wrote first this term, the terms that had alpha in them. So for this term, ui minus 1, we wrote it here. And then we had this V alpha minus 1 term, which is coming from here. We just wrote the Taylor series expansion for that and the diffusion term, which is here. And then some of the terms cancel out as we expect. And what we finally got are these three equations. And, and finally, we got to this equation, okay? And in this equation, the first two terms are just our governing equation, the equations that we wanted to solve, okay? And then the other terms, as you see, we call them to truncation error. So these are the truncation error for this approximation. So we wanted to know what is the order of accuracy for this truncation error problem. So if we see if alpha is 0, so this is 0, this is 0, the order of the accuracy is going to be delta x squared, right? From these two terms, we can say that. And the question was, what about if alpha is not 0? What would be the order of the accuracy? Is it going to be order delta x or other things? So the question we kind of mentioned was, can we choose alpha such that to increase the order of the accuracy of this approximation? So the first thing we did, we just said, okay, I'm gonna use this equation, and this gives me this relation for u double prime equals to v over du prime I, and similarly for higher order, higher derivatives. And so I just wrote everything by writing it based on all the derivatives here based on u double prime I, and factored u double prime I here for the truncation error, and got to these terms, multiplied them by 1 over d, and I wanted to set all the terms that have delta x squared to 0, okay? So then I can get a higher order accuracy, which is delta x cubed. So I define Péclet number as v delta x over d, delta x over d. Then this led to me to this equation, Péclet number minus alpha over 2 Péclet number plus 1 over 12 Péclet number square. And if we choose Péclet over 2, alpha to be Péclet over 6, if we choose alpha to be Péclet over 6, then the approximation is going to give me ordel delta x cubed, because this is going to be 0, right? And we are only left with this. So then we went further and said, how about higher order? Can we choose alpha such that to be able to have a higher order approximation for this problem? And we found, okay, if we write everything based on u prime I, all the terms, we are gonna be left with these two terms, and also based on Péclet number. And then if we are able to set this to 0, if we choose a proper alpha. So if we choose alpha to be this, then the truncation error is going to be 0. And we found you can write this as this sum or this series. You can simplify it based on this relation here. And so this alpha is going to make the truncation error to be 0, and this finite difference approximation gives the exact solution for the considered PDE. So we were able to make the PDE, the finite difference approximation, exact by choosing this alpha value. Okay, thank you very much, everyone.